In recent years, artificial intelligence, AI, has made significant progress thanks to tools and algorithms that are able to analyze data, recognize patterns and make predictions with an accuracy that was unimaginable a few decades ago. But the question arises, are these tools good enough, or should we turn to advanced technologies such as quantum computing? Arguments for existing AI tools. AI tools have proven their value in various sectors, from healthcare and finance to transportation and entertainment. Machine learning can process vast amounts of data and improve over time. Deep learning, a subset of machine learning, has seen the development of neural networks that can recognize patterns and make decisions with high accuracy. These tools have proven successful in solving complex problems and are constantly improving. In addition, these AI tools are accessible and practical. They work on classic computers, which are widely available and comparatively affordable. They can be used in real-world applications today and offer immediate benefits for businesses and society. Given the power of existing AI models, quantum computing support may not be urgently needed. The quantum leap, potential and challenges. Quantum computing is often touted as the next big thing in AI. Quantum computers can process an immense number of possibilities simultaneously, which could potentially enable the acceleration of AI algorithms and more efficient processing of larger data sets, leading to more powerful AI models. A recent study by the Boston Consulting Group identified a market potential of $50 to $100 billion for quantum opportunities in generative, basic and horizontal AI, which could impact virtually all industries. According to BCG, there are additional multi-billion-dollar opportunities in the prevention of fraud and money laundering as well as algorithms for AI in the automotive sector. However, quantum computing is still in its infancy. Today's quantum computers have a limited number of qubits, and maintaining their quantum state, known as coherence, is a significant challenge that limits the complexity of the computations that can be performed. Furthermore, quantum computers are not simply an update of classical computers, they require entirely new algorithms. For example, classical machine learning models such as neural networks are trained by adjusting parameters, weights and offsets, based on the input data to minimize the difference between the model's predictions and the actual output. Sophisticated models have millions or billions of parameters and are tuned through a process called gradient descent, determining the direction in which changing the parameters will minimize this difference. However, measuring or estimating gradients in a quantum computer is extremely difficult. Therefore, trying to use a classical algorithm on a quantum computer is doomed to failure and new algorithms are needed. The development of these algorithms is a complex task which, although promising, is still in its early stages. For example, a new type of machine learning algorithm called reservoir computing appears to utilize unique quantum properties to achieve good results in classification and prediction applications. Quantum computing and generative models. One area where quantum computers are excelling today is in the generation of randomness. In classical computers, random numbers are generated using algorithms or from external sources of randomness, such as atmospheric noise, but these numbers are not truly random. If you know the algorithm and its initial conditions, called the seed, you can predict all the numbers that the algorithm will generate. In contrast, quantum computers can generate truly random numbers thanks to core principles of quantum mechanics, such as superposition. Superposition shows that a quantum bit can exist in multiple states simultaneously, and when measured, the result is inherently random. Generative modeling, an unsupervised machine learning scheme, can benefit from this randomness. Quantum computers can generate statistical correlations that are otherwise very difficult to replicate, making them ideal for this application. Such generative models can be used in numerous problems, such as portfolio optimization, where the generative model attempts to replicate high-performing portfolios discovered by the algorithm, resulting in portfolios with much lower risk than those discovered by classical algorithms. Similar applications have been proposed for molecular generation, drug discovery and even factory floor planning. The future of quantum computing and AI. Despite these early challenges, the potential of quantum computing for AI is enormous. Quantum machine learning could classify larger datasets in less time, and quantum neural networks could process information in ways that classical neural networks cannot. While existing AI tools are powerful and practical for many applications today, quantum computing represents a promising frontier with the potential to significantly advance the field. Nevertheless, the road to practical quantum computing is long and fraught with challenges. It will probably be some time before quantum computers are more powerful and ready for widespread use in AI. Until then, the focus may be on maximizing the capabilities of our existing AI tools as we continue to explore the exciting possibilities that quantum computing offers.